Here's a strange thought to fall asleep on tonight. Somewhere out there, right now, there's a planet where it rains iron. Not metaphorically, not poetically, actually iron, vaporized by unbearable heat on one side of the world, carried by howling winds, and condensed back into droplets on the other. For a long time, that would have sounded like something from a myth. Today, it's simply a measurement, confirmed by real telescopes pointed at a real, distant world. So here's the question worth carrying with you tonight. If a planet can rain metal, what else might be quietly true out there that we simply haven't had the imagination to guess yet? Hello, and welcome to Somniora Mind. I'm glad you're here. Hold that question loosely tonight, because we're going to let a few more sit alongside it. Why might a planet's own crust sometimes rise up and become its sky? Why does a whole family of planets sometimes vanish, one by one, until only a single lonely survivor remains circling its star? And how can a world without any sun at all, wandering forever through the dark between galaxies, still manage to keep a hidden ocean of liquid water sealed away inside it? We're not going to rush toward answering any of those tonight. Over the next while, we're going to drift slowly through some of the strangest planets scientists have ever found. Worlds stretched into the shape of an egg, worlds with two sunsets, worlds so puffed up and light they could almost float on water, and worlds that seem to defy the very idea of what a planet is supposed to be. There's no test at the end of this, and nowhere you need to arrive. If your attention starts to loosen along the way, that's exactly what this is for. Let the strange facts drift past like something half-heard through a wall, and let yourself sink. If this kind of slow, quiet wandering helps you rest, stay close, and we'll keep exploring together, one quiet mind at a time. Now let your shoulders soften, let your eyes rest, and let's drift out past the edge of our own solar system, into a universe far stranger than the one we grew up imagining. One of the strangest ideas in modern astronomy is that rain doesn't have to be water. On a particular scorching exoplanet, the side permanently facing its star is so hot that iron itself vaporizes directly into the atmosphere. Powerful winds then sweep that iron vapor across to the planet's permanent night side, where temperatures finally drop low enough for it to condense back into droplets. In other words, this world may have weather made of metal, not in any gentle, silvery way the phrase might suggest, but as part of an infernal, ongoing cycle of heat, wind, and condensation utterly unlike anything found on Earth. The planet is locked to its star, meaning one side bakes in permanent daylight while the other sits in permanent darkness, and that stark, unmoving contrast is exactly what drives the whole strange process. What makes it so gripping is that it sounds like pure fantasy, and yet it comes directly from real observations of a real, distant world. Even the word weather starts to feel far too gentle for something this extreme. This particular planet is far from a lonely curiosity, either. A number of giant worlds live so close to their stars that our ordinary ideas about weather simply stop applying. On these planets, heat isn't just fierce, it's transformational. Temperatures can climb high enough to tear molecules apart entirely, turning metals directly into vapor. Iron, magnesium, and other heavy elements may drift through the atmosphere like ghostly gases. A rocky mountain, if one somehow existed there, couldn't survive. It would soften, begin to glow, and eventually simply become part of the air itself. Astronomers call these worlds ultra-hot Jupiters, though the name barely prepares you for what they actually are. They race around their stars on blisteringly tight orbits, enduring a constant flood of radiation. For researchers, they've become extraordinary natural laboratories, letting scientists watch chemistry unfold under conditions no world in our own solar system could ever match, and discover just how much stranger a planet can be than anyone once expected. Not every extreme world is a gas giant, either. One rocky planet, orbiting so close to its star that Earth would feel impossibly mild by comparison, may have a surface covered in a vast, glowing ocean of molten rock. Picture a horizon made not of water, but of liquid stone, glowing orange and red beneath a dark sky. This world is likely locked in place, always showing the same face to its star, so that one side receives intense, unrelenting heating again and again, while the rest of the planet struggles endlessly to redistribute that energy. Astronomers have even found hints that it may hold an atmosphere rich in gases released directly from its own molten interior, which matters because it suggests this isn't simply a dead cinder drifting through space. It may still be geologically active, magma, gas, and heat locked together in a fierce, ongoing exchange. Not a hot rock, in other words, but something closer to a living furnace, endlessly reshaping itself beneath a sun that never lets up. Gravity, at close enough range, can do more than simply hold a planet in orbit. It can begin to reshape the planet itself. One well-known world sits so close to its star that gravity is visibly pulling it out of its natural round shape, stretching it instead into something closer to an egg or a football. That alone would be extraordinary on its own. But the story goes further, because that same gravitational strain is also helping to strip material away from the planet entirely, drawing gas outward toward the star and slowly, patiently tearing the whole world apart. This isn't merely a misshapen planet. It's a planet caught under visible, ongoing stress, distorted and gradually consumed by the very star it orbits. Its entire year lasts just a little over a single Earth day, which tells you exactly how brutally close it has to be. We tend to think of planets as stable, settled things, shaped once by gravity and then left largely alone. This world quietly shows the opposite. A planet can be deformed, heated, and slowly eroded until it becomes something temporary and, in its own way, tragic, a place caught in the very act of losing itself. And some worlds don't reflect their star's light back at all. They simply seem to swallow it. One particular gas giant counts among the darkest planets ever found, reflecting so little starlight that it's genuinely darker than coal. It doesn't shine back into space the way we'd expect a planet to. Instead, it seems to absorb starlight almost completely, leaving behind only a faint red glow from its own residual heat. That darkness isn't just eerie, it's scientifically thrilling. Something within the planet's atmosphere appears to actively absorb light rather than reflect it, and even though the world itself is hot enough to visibly glow, it suggests that clouds, chemistry, and light can combine in ways that feel almost unnatural to us. A planet, it turns out, can be burning hot and still look pitch black. That contradiction is part of exactly what makes these strange worlds so endlessly fascinating to sit with. They don't simply offer new places to imagine. They quietly force new meanings onto words we thought we already understood completely. Words like dark and day and sky. For centuries, the idea of a double sunset belonged strictly to myth and fiction. Then astronomy caught up with the imagination. Some planets really do circle two stars at once, tracing wide, patient paths around stellar pairs that are themselves locked in orbit around each other. One of the first confirmed examples to genuinely capture the public imagination was a world where two suns would hang together in the same sky. It's hard to overstate how much that single discovery changed the emotional feel of the universe. A solar system, it turned out, no longer had to look like ours. It could be built instead around a partnership. Days, seasons, and shadows on a world like that would be shaped by two separate, moving sources of light, rather than one fixed, dependable sun, and even the sky itself would feel a little less predictable. These planets also proved something important about nature more broadly, that planet formation is tougher and considerably more creative than we once assumed. Even in a place where two stars are constantly tugging at the surrounding material, worlds can still emerge and hold stable orbits for ages, quietly circling both suns together. Not every planet belongs to a star at all, though. Most planets orbit a sun, keep to a family, and move through space as part of a system. Rogue planets break that picture completely. These are worlds that drift alone through the galaxy, entirely untethered to any star. Some may have formed around a sun and then been flung outward by gravitational chaos, cast out during violent encounters with larger planets or passing stars. Others may have formed in isolation from the very start, more like failed stars than escaped planets. Either way, they wander through the darkness on journeys that can last billions of years. At first glance, a world like this seems hopelessly dead, but it may not be quite that simple. A thick atmosphere and leftover internal heat could keep some rogue planets warmer than you'd expect, especially deep beneath the surface. That possibility makes them feel even stranger. A planet, it turns out, doesn't always need a sunrise to remain a genuine world. Sometimes it can carry its own hidden story quietly through the dark. Some worlds, meanwhile, orbit stars that are already dead, and by every reasonable expectation, shouldn't have survived to see it. When a star dies, it doesn't always go peacefully. It swells, sheds its outer layers violently, and leaves behind a dense stellar remnant, a white dwarf, or perhaps a pulsar, which is exactly what makes the discovery of planets around these stellar corpses so astonishing. In many cases, those planets should have been consumed entirely during the star's violent transformation. And yet, some are still there. They either survived genuinely impossible odds, or they formed afterward, out of the debris left behind. Both possibilities are remarkable. A planet that survives an event like that has lived through the destruction of the very system that created it. A planet that forms afterward is stranger still, because it means planetary birth can happen even in the ashes of stellar death. These aren't ordinary solar systems, they're afterlives. They remind us that the story of a planet doesn't always begin quietly in gas around a young, calm star. Sometimes it continues after disaster, in a place where almost everything familiar should already have ended. There's at least one famous exoplanet candidate that sounds almost mythic in its origin, a dense world that may have formed directly from the wreckage of a destroyed star. Some astronomers believe the planet orbiting a particular pulsar is the carbon-rich remnant of a once much larger companion star, gradually stripped away until only its hardened core remained. If that interpretation holds up, this isn't merely a planet in the ordinary sense at all. It's a stellar remnant, effectively recast at planetary scale. It may be packed with crystalline carbon under such extreme pressure that the phrase "diamond world" made its way into public imagination. Whether or not that particular image is fully accurate, the deeper truth is astonishing enough on its own. A world may exist that wasn't gently assembled from dust in a young disk at all, but carved instead out of the death of a star by gravity, radiation, and time. Planets, it turns out, can arise from birth, but they can also arise from ruin. A year on Earth feels natural because it matches the rhythm of our seasons and our lives. But some planets complete a full orbit so fast that an entire year passes in less time than a single Earth day. These worlds cling so tightly to their stars that gravity keeps them in relentless, unbroken motion, circling again and again at distances that would have seemed impossible to imagine. One orbit ends, and another begins almost immediately. This changes everything about how a planet like this could exist. The star would loom enormous in the sky. Heat would become genuinely overwhelming. Tidal forces would likely lock one entire hemisphere into constant, unbroken daylight. Whatever thin atmosphere might exist would have to cope with extremes our own solar system barely hints at. What's so captivating here is the total collapse of familiar scales. On worlds like this, the very phrase, "next year," simply loses its meaning. Time itself starts to feel different when a planet races through an entire orbit faster than Earth spins through one ordinary day. Some planets stay locked in place relative to their star for an entirely different reason, one connected less to speed and more to gravity's patient, steady pull over time. When a planet orbits close enough to its star for long enough, gravity can gradually slow its rotation until the very same hemisphere always faces inward. One side lives permanently beneath a fixed sun that never sets. The other remains in endless darkness, with no dawn and no memory of what noon even feels like. This isn't a rare poetic idea. It may actually be quite common among close-orbiting exoplanets. The consequences are dramatic. The star-facing side can grow hot enough to melt rock outright, while the far side may plunge into cold severe enough to freeze gases straight out of the air. Between the two extremes lies a narrow twilight zone, a belt where conditions might be somewhat calmer, though still swept by violent winds constantly working to balance the planet's extremes. On Earth, sunrise and sunset quietly shape how we experience time itself. On worlds like this, time works differently. Light becomes geography. A person standing still wouldn't simply wait for day to end. They'd have to travel to escape it entirely. Not every planet travels on a neat, nearly circular path the way Earth does, either. Some follow highly elongated orbits instead, ones that carry them in close to their star before flinging them far back out again. Which means a single year on such a world can include enormous swings in both temperature and available energy. A planet might spend part of its orbit in comparative chill, then rush inward and experience a surge of heating so extreme that its atmosphere visibly expands, its chemistry shifts, and any stable weather pattern gets thrown into total confusion. This isn't simply a longer winter followed by a longer summer. It's a planet moving between two genuinely different physical states as it loops repeatedly around its star. The changing distance affects light, heat, and even wind patterns in ways that would make Earth's climate look almost impossibly calm by comparison. Worlds like this are thrilling precisely because they show that a year can be a drama, not a simple, gentle cycle. Orbit itself becomes an engine of planetary upheaval, quietly rewriting the climate again and again with every pass. Seasons, too, can behave very differently depending on how a planet happens to lean. On Earth, our seasons come from the tilt of our axis, giving us a fairly reliable, familiar cycle of changing sunlight throughout the year. But some planets may experience far more dramatic seasonal swings if their axes are tipped at much more extreme angles. Imagine a world leaning so far over that one pole points almost directly at its star for part of the year, while the other pole sinks into long, unbroken darkness. A planet like that wouldn't have anything resembling our familiar spring, summer, autumn, and winter. It might instead swing between months of relentless heating and months of deep freeze, with strange, unstable transition periods in between. The star's path across the sky would feel unnatural too, perhaps circling endlessly around the horizon, or vanishing from view for long stretches at a time. Climate on a world like this could be extraordinarily difficult to predict, especially if oceans, clouds, or thick air were redistributing heat in unusual ways. It's a quiet reminder that a season isn't some universal, guaranteed experience. It's simply a local consequence of exactly how a particular world happens to lean. And there are planets stranger still, ones where the ordinary relationship between day and year breaks down entirely. On Earth, a single day is much shorter than a year, so the whole rhythm feels natural and easy to trust. But on certain exoplanets, that balance can actually reverse. A planet can rotate so slowly that one full turn on its own axis takes longer than a single complete orbit around its star. In other words, its day is genuinely longer than its year. That sounds impossible at first, but it's a real, physically grounded consequence of certain orbital and rotational dynamics under the right conditions. A world like that would experience sunlight in a profoundly unfamiliar way. The star's position in the sky would shift through a strange, ongoing contest between the planet's slow spin and its comparatively faster orbit. Time itself would stop feeling intuitive at all. The basic units that quietly guide life here on Earth simply wouldn't line up in any comfortable, recognizable pattern. A few exoplanets are so swollen and airy that they almost seem physically impossible. They're enormous in size, sometimes even wider than Jupiter, and yet their actual mass is astonishingly low. If you could somehow place one into a large enough ocean, it might genuinely float. That sounds playful, but the physics underneath it is serious and genuinely strange. Astronomers call these worlds superpuffs, and they seem wrapped in vast envelopes of hydrogen and helium that stretch out far from their cores. Their gravity is so weak at the outer edge that the atmosphere balloons dramatically outward, giving the whole planet a strange, ghost-like bulk. One especially well-known example has been described as a planet with the breadth of a gas giant and the density of spun sugar. Planets like these genuinely challenge our formation models because they look fragile, inflated, and somehow temporary, less like solid worlds and more like drifting celestial mirages, enormous in silhouette, yet barely holding themselves together at all. A superpuff planet may actually be one of the more misleading objects in all of astronomy. Judging only from its size, you might expect a massive world with crushing gravity and a thick, deep interior. Instead, some appear to be built around surprisingly small cores, wrapped in vast, ballooning shells of gas. The atmosphere does nearly all the visual work here, expanding outward and making the planet appear grand and swollen, while the hidden center may be only a modest fraction of the total apparent size. That structure is fascinating because it hints at very delicate timing somewhere in the planet's history. The core had to gather enough gas before the surrounding disk around its star fully dissipated, but not so much that it simply became an ordinary giant instead. Something unusual clearly happened, and the result is a world that feels, in a real sense, exaggerated, almost all outer presence, with relatively little inner bulk. It's a quiet reminder that planets can't always be judged well by their outline alone. A huge planetary radius can conceal something surprisingly slight hiding beneath the clouds. Some worlds, meanwhile, feel less like complete planets and more like remnants of something once far larger. Certain exoplanets are extremely dense, sit very close to their stars, and appear so thoroughly stripped down that astronomers suspect they may be the surviving cores of much larger planets. Picture a world once wrapped in deep gas or volatile-rich outer layers, orbiting too near a star that gradually cooked and blew those outer regions away into space entirely. What remains could be the core, compressed, battered, and finally left exposed after billions of years of steady loss. This idea is powerful because it gives certain planets a biography built entirely on attrition. We're not simply seeing how a world forms. We're seeing how a world can be slowly peeled back, layer by layer, until only its innermost part remains. It also changes how we look at small, rocky planets orbiting close to their stars. Some may not be pristine little Earths at all. They may instead be the leftover hearts of once giant worlds, surviving quietly after nearly everything else about them was erased. Not every planet loses its atmosphere gently, either. A star does more than simply shine. It also blows a steady stream of charged particles outward, and on some planets, that wind may be fierce enough to actively erode the atmosphere itself. Worlds orbiting close to particularly active stars are especially vulnerable. Over long stretches of time, their upper air can be heated, ionized, and gradually carried off entirely into space. This slow process can transform a planet's entire fate. A world that once had a thick envelope of gas may be left bare, dry, and far more exposed than it once was. The violence unfolds slowly by human standards, but relentlessly, turning long-term habitability into an ongoing race between atmospheric replenishment and constant stellar attack. For astronomers, these stripped atmospheres aren't simply losses, they're valuable clues. By watching gas escape a planet, scientists can infer the strength of its star's wind and just how fragile that planet's air really was to begin with. A planet's sky, it turns out, isn't always something stable and dependable. Sometimes, it's something the star itself is actively trying to steal. At the far end of that same process sit planets caught in the act of genuinely coming apart. There comes a point where tidal force stops behaving like a sculptor and starts behaving more like an executioner. If a planet drifts too close to its star, gravity can begin actively stripping material away from it entirely, especially if the world was already fragile or loosely held together to begin with. Rock, gas, or dust may stream steadily outward, forming long tails that trace the destruction as it unfolds. In some cases, astronomers have found direct evidence for disintegrating worlds that appear to be shedding material orbit after orbit. It's one of the most dramatic fates a planet can suffer. Rather than exploding in one single, sudden instant, it comes apart instead piece by piece, slowly unmade by the very same gravity that once kept it steadily in motion. A planet, in other words, doesn't always die by impact or fire. Sometimes it dies through erosion on a cosmic scale, crumbling gradually under relentless pull, transformed from a solid place into a slowly drifting trail of debris, still faintly circling even as it quietly vanishes. Earth feels genuinely like a water world, right up until you compare it against what may exist elsewhere. Some exoplanets could be wrapped in global oceans hundreds, or even thousands, of miles deep, with no continents at all, no shorelines, and no familiar meeting place between land and sea. On worlds like this, a descent downward wouldn't end at a rocky seabed the way it does here. Pressure would climb to such extremes that water itself could transform into exotic, unfamiliar forms of ice, even while the temperatures directly above stayed high enough for liquid layers to persist. Which means a planet could hold an ordinary ocean, then a buried shell of compressed ice underneath it, then solid rock far below that. It's a beautiful and slightly unsettling arrangement. Worlds like this might look perfectly calm from space, blue and serene, while their interiors are quietly stacked in layers unlike anything found on Earth. They stretch the meaning of the word ocean well beyond its usual boundaries. Sea, on a world like this, doesn't have to mean beaches and gentle tides. Sometimes it simply means a planet almost entirely claimed by water, top to bottom. Even a planet without any star at all might still manage to keep some liquid water hidden away. The phrase liquid water usually brings sunlight to mind, beaches, rivers, or at least a warm, dependable star somewhere overhead. But a rogue planet, wandering alone through interstellar darkness, may not need any of that, if the underlying conditions happen to be right. Beneath a thick atmosphere or under a crust of insulating ice, leftover internal heat could still be enough to keep water in liquid form far below the surface, which means one of the most important ingredients for life, as far as we understand it, might exist on a world where no sunrise has occurred for billions of years. That water wouldn't glitter, and it wouldn't lie beneath clouds lit by any sun. It would remain instead in total darkness, hidden and sealed away from the universe outside. That possibility is genuinely astonishing, because it widens our whole map of where life-friendly conditions might exist at all. Habitability starts to feel less about location and more about structure. A planet can leave its star behind entirely and still protect an inner sea. Somewhere out there, the galaxy may contain warm, wet worlds quietly drifting through absolute, endless night. Some rocky planets, meanwhile, orbit so close to their stars that their surfaces never fully cool and harden at all. Instead of continents, valleys, and gentle seas of water, they may host vast, glowing pools of molten rock spread across their permanent dayside, like inland oceans made entirely of fire. These magma seas aren't simply a surface detail, they may shape the entire behavior of the world. Liquid rock can absorb heat, circulate slowly, release gases, and interact with whatever thin atmosphere hovers above it, which means the ordinary boundary between geology and weather starts to genuinely blur. On a world like this, you wouldn't see waves breaking gently on a shore, but perhaps a horizon of slowly moving fire instead. Some of these worlds may even have rock vapor rising directly off the molten surface, only to condense again somewhere else nearby. The result is a planet that behaves less like a solid, settled place, and more like an active furnace, still very much a world, but one caught somewhere halfway between planet and eruption. Some planets that look calm and cloud-covered from a distance may be hiding something far more turbulent below their skies. High in the atmosphere, clouds of exotic material could drift comfortably through relatively cooler layers, while far beneath them, temperatures climb steadily into genuinely brutal territory. The visible cloud deck becomes, in effect, a kind of false surface, quietly concealing a deep furnace below. This contrast is part of what makes giant planets so hypnotic to think about. What looks entirely serene from above may sit directly over pressures and heat that defy easy imagination. On a hot giant, clouds might form from silicate particles, metals, or condensed minerals, floating far above layers where the atmosphere grows dense, compressed, and genuinely savage. A world can appear wrapped in pale, gentle brightness while hiding conditions closer to an industrial blast furnace underneath. The beauty, in a case like that, is entirely real, but only skin deep. Below the clouds, the planet may be all violence. And some planets don't cooperate with our curiosity at all, wrapping themselves instead in hazes that hide nearly everything below. Astronomers often want to peer deep into an exoplanet's atmosphere, but some worlds simply refuse. They're cloaked in high hazes made of tiny particles that scatter light so effectively they block any real view of the layers underneath. This can turn an otherwise promising target into a lingering mystery. The planet is there, the atmosphere is there, but the finer details stay hidden behind a veil. These hazes may be produced by complex chemistry driven by ultraviolet light, or by the condensation of exotic materials high above the deeper, more active weather systems. The result is a world whose visible character is shaped not by what lies below, but by a suspended curtain hanging in its upper air. It's a beautiful kind of frustration for scientists. A giant planet can keep its deepest secrets simply by growing a thick enough haze. Even with our most advanced telescopes, some worlds remain little more than silhouettes. Their atmospheres only partly readable, like faces glimpsed through frosted glass. Earth's crust feels ordinary only because it happens to be home. In truth, the minerals that dominate our own planet reflect a very specific history of temperature, chemistry, water, and geological activity. Change those underlying ingredients even slightly, and an entirely different kind of rocky world could emerge instead. Some exoplanets may have crusts rich in minerals that are genuinely rare here on Earth's surface, shaped by hotter conditions, unusual elemental ratios, or simply the total absence of water-based weathering. On a carbon-rich world, for instance, the upper layers might include forms of carbon-bearing rock far more abundant than anything common here at home. On an ultra-hot rocky planet, the surface itself could be built entirely from minerals that are only stable under truly brutal heat, with familiar Earth rocks unable to survive there for very long at all. This matters because a planet's crust isn't merely scenery. It controls how a world reflects light, releases gases, stores heat, and changes over time. Even stone itself, it turns out, may tell very different stories on genuinely strange planets. Under just the right conditions, a carbon-rich planet may do something almost unbelievable. Deep inside, immense pressure could squeeze carbon into crystal structures resembling diamond, while shallower layers might hold graphite or other carbon-heavy materials instead. This doesn't mean a sparkling jewel world simply waiting to be mined. It means a planet whose interior geology could be shaped by the very same element that forms both soot and gemstones here on Earth, but on a scale that defies ordinary thought entirely. The deeper you go, the more pressure transforms simple chemistry into something harder and considerably stranger. That possibility matters because it shows just how much a planet's interior depends on its starting composition, not simply its size. A world built from a genuinely different elemental foundation may not just look different at the surface. It may be fundamentally different all the way down. Beneath an alien crust, entire layers of carbon could be stacked like an unfamiliar geological poem, written under crushing pressure and unimaginable stretches of time. Clouds themselves sound comforting, right up until you remember that a cloud is really just whatever the local environment happens to allow to condense. On Earth, that usually means water. On a far hotter planet, the raw materials involved can be utterly different. Some exoplanets may form clouds out of silicate particles, the same broad family of materials that helps make sand, rock, and ordinary glass here at home. High in the atmosphere, where temperature and pressure reach exactly the right balance, those substances may condense into fine mineral grains and drift through the sky like an entirely alien weather system. Imagine looking upward and knowing that the clouds above you aren't wet, soft, or cool at all, but composed instead of tiny specks of rock. On certain worlds, clouds like this may even glow softly, scatter starlight in unusual colors, or help control how heat moves through the atmosphere overall. They make the familiar shape of a cloud feel entirely, newly strange. A cloud, it turns out, isn't defined by softness. It's defined by suspension. Even powdered stone can float when a world is strange enough to allow it. No one has ever stood on the surface of an exoplanet and actually taken a breath, but basic chemistry lets us imagine, at least loosely, what the air on some of these worlds might genuinely smell like. On a hot, rocky planet with volcanic gases constantly rising into its atmosphere, sulfur compounds could dominate, giving the air a sharp sting somewhere between struck matches and rotten eggs. On a scorched gas giant with vaporized metals high in its sky, the air might carry something harsher still, closer to a furnace or hot machinery than to anything organic. On worlds where silicate and mineral gases lift directly off molten surfaces, the smell might resemble stone dust, ash, or rock fresh from a kiln. Of course, many of these atmospheres would be lethal long before scent ever mattered to anyone. That's part of what makes the idea so gripping. Smell is deeply intimate. It makes a distant, abstract world suddenly feel physical, present, and real. The universe, it turns out, isn't only full of strange places to look at. It may be full of strange air too, each with its own distinct chemical signature quietly waiting out there in the dark. One of the great triumphs of modern astronomy is that we've genuinely learned to read the chemistry of worlds we can never actually visit. As an exoplanet passes directly in front of its star, a small fraction of starlight filters straight through its atmosphere, and different molecules leave behind different, telltale marks in that light. That's exactly how astronomers have found real signs of water vapor, carbon dioxide, sodium, potassium, and even hints of metal-bearing gases in distant, unreachable skies. It's a remarkable achievement when you stop and really sit with it. We're no longer simply finding planets anymore. We're sampling their air from clear across light years of empty space. Each new detection transforms a distant world from a simple dot of light into a genuine place, one with real weather, real chemistry, and its own physical character. Some atmospheres appear hazy. Some seem particularly enriched in specific elements. Some remain frustratingly hard to fully decode. But the larger revelation underneath all of it is already profound. A distant planet's sky is no longer entirely unknowable. It can leave behind a chemical signature, quietly written into passing starlight. And on some tidally locked worlds, that atmospheric chemistry doesn't even stay the same all the way around the planet. The side turning gradually into day and the side turning gradually into night may not actually share the same atmospheric chemistry at all. As gas circulates steadily around a planet, molecules can form, break apart, condense, or reappear entirely, depending on local temperature at that particular moment. Which means the atmosphere on the morning side, where gases are just emerging from cooler darkness, may genuinely differ from the atmosphere on the evening side, where the same gases have just endured hours of intense heating. This is one of the strangest refinements to come out of exoplanet science in recent years. We're no longer simply asking what chemicals a given planet has. We're asking how those chemicals actually vary across the whole globe. A world can carry different atmospheric personalities, depending entirely on which limb of the planet you happen to be observing at the time. The effect turns a planet into something considerably more dynamic than a single average description. It has regions. It has transitions. It has moving zones of ongoing chemical change. Even the sky, it turns out, can have a kind of daily geography, with sunrise and sunset each leaving behind their own distinct fingerprint on the air. Some planetary systems make our own solar system look positively spacious by comparison. Astronomers have found stars surrounded by multiple planets, all crowded together into a region smaller than Mercury's own orbit around our Sun. Picture several full worlds circling steadily within the space we'd normally assign to just one. Their skies, if they had visible horizons at all, might be genuinely haunted by neighboring planets looming far larger overhead than Venus ever appears from Earth. In systems built this way, gravity writes a far more intricate score. Each planet constantly feels the pull of all the others. Their orbits gradually settle into delicate, interlocking patterns that can remain stable for ages, provided every single world keeps nearly perfect time. It's one of the most thrilling lessons to come out of exoplanet discovery. Solar systems don't actually need broad spacing to survive. Nature can build them compact, intricate, and genuinely beautiful, almost like a clockwork city quietly circling a single sun. The result isn't chaos at all, but a kind of compressed elegance, where many worlds live astonishingly close together without immediately tearing one another apart. One of the clearest, most famous examples of this kind of planetary crowding is a system where several Earth-sized worlds circle a tiny, dim red star at distances that would all comfortably fit well inside Mercury's own orbit. Because the star itself is so faint, though, those tightly packed paths don't automatically turn the planets into furnaces the way you might expect. Instead, it creates a strange inversion of our usual intuitions. A region that would be impossibly hot around our own sun can comfortably host an entire family of worlds around a considerably dimmer star instead. The planets pass close by one another and tug gently on each other in rhythmic patterns, locked into a chain of resonances that keeps their whole motion carefully ordered. This gives the system an almost musical quality, as though each world is quietly keeping time with the one beside it. It's a gentle reminder that the true scale of a solar system depends heavily on its star. A tiny sun, it turns out, can host a packed, intimate architecture that still leaves plenty of room for astonishing variety. Some planetary systems achieve a kind of gravitational choreography, so precise that neighboring worlds fall naturally into resonance with one another. One planet may orbit twice for every 3 orbits of another, or follow some other steady, repeating ratio that keeps their mutual pulls organized rather than chaotic. This matters because resonance isn't merely a mathematical curiosity, it reveals real history. Planets often settle into these patterns while migrating slowly through their birth disk early in a system's life, gradually becoming locked together as they move. Once established, that resonance can preserve long-term stability and create an elegant, ongoing chain of repeated motion. From the surface of a planet like this, if anyone could watch the neighboring worlds over sufficiently long stretches of time, their appearances would recur with an almost uncanny regularity, as though the whole system were quietly keeping its own beat. What makes this so beautiful is that gravity alone creates the entire pattern. No hand arranges it deliberately. The planets simply fall into rhythm on their own, and the whole solar system begins to behave less like a crowd and more like a piece of music. Because planets in tightly packed systems pull on one another so precisely, their orbits sometimes shift in small, telltale ways that astronomers have learned to read like clues. A transit is supposed to happen right on schedule. If a planet crosses in front of its star every 10 days, then the next dip in starlight should arrive exactly on time. But in some systems, it simply doesn't. The transit arrives a little early or a little late because another nearby planet is gently tugging on the transiting world and subtly changing its orbit. These transit timing variations turn out to be incredibly useful. They can reveal planets that don't transit at all themselves, and they let astronomers weigh distant worlds simply through their mutual gravitational influence on each other. What makes this so satisfying is how the method quietly turns punctuality itself into evidence. A tiny delay or a tiny advance in a distant shadow becomes the clue that another, unseen planet is out there, pulling gently from the side. We learn about hidden worlds not by seeing them directly, but by noticing that another world simply missed its expected cue. In astronomy, it turns out, even being a little late can become its own quiet form of revelation. The planetary systems we observe calmly today may actually be the survivors of far more crowded, far more chaotic beginnings. Early on, many stars may well have hosted additional worlds that later collided with one another, were swallowed whole by the star, or were ejected entirely into interstellar space. What remains today can look perfectly calm, but that calm may be deeply deceptive. A neat, modern-looking arrangement may simply be the residue left over from ancient instability. This idea gives entire systems a quiet sense of lost history. A star with 3 planets today may once have had 5 or 7 or more, with close gravitational encounters gradually removing the losers over time. Giant planets may have bulldozed their way through inner systems. Smaller rocky worlds may have merged together into larger ones. Some of the rogue planets currently drifting through the galaxy may well be the missing members of families exactly like this one. It's a powerful shift in perspective. When we look at a settled system today, we may only be seeing the final cast, not the full original ensemble. Every quiet, stable orbit we observe may be quietly hiding a much louder past. Planetary systems, in other words, aren't always graceful. In their youth, and sometimes long afterward too, they can become crowded arenas where worlds cross paths, clip each other's orbits, and eventually collide. Some collisions may shatter both planets entirely into drifting debris. Others may fuse them together into a single larger world, built from fire, shock, and molten wreckage. And in still harsher systems, a planet may simply be driven so close to its star that it ends up swallowed whole. This isn't speculation born purely from a taste for drama. Our own solar system carries clear signs of ancient violence in its own past, and exoplanet systems can be even more unstable than ours. A planet that exists calmly today may be the surviving result of much earlier destruction. Its current orbit may have been cleared entirely by past impact. Its mass may quietly hide the remains of another world it long ago absorbed. That makes every quiet, settled planet feel considerably more layered than it first appears. A calm present can rest directly on top of a genuinely catastrophic past, and the worlds we find today may simply be the polished survivors of astonishing acts of planetary violence. Some planets orbit stars far older than our own sun. Our sun, by stellar standards, is really only middle-aged. Yet certain planets circle stars that have been quietly shining for far, far longer. Which means there are worlds out there in the galaxy that may have existed while Earth itself was still assembling, or even before our own sun had been born at all. One especially famous example orbits a star sometimes nicknamed for its extreme age, because the system itself may be more than 12 billion years old. To imagine a planet that ancient is to feel time expand in a genuinely new direction. This world may have witnessed the galaxy in a much earlier state, back when heavy elements were considerably rarer, and the Milky Way itself was still young. Ancient planets like this matter because they help test our entire timeline for planetary formation. They suggest that worlds began appearing very early indeed in cosmic history, that the universe may have been quietly building planets for almost as long as it's had stars at all, which makes our own comparatively young world feel late and wonderfully recent by comparison. Some worlds, meanwhile, have survived events that seem, on the surface, like they simply shouldn't be survivable at all. When a massive star explodes as a supernova, the event releases staggering amounts of energy, hurls material violently outward into space, and instantly transforms the entire system around it. It feels, from any reasonable perspective, like the end of everything nearby. And yet, some planets may genuinely survive an event like that, especially if they orbit far enough away, or if their exact position and timing happen to be fortunate. Survival, in a case like this, wouldn't mean staying entirely unchanged, of course. The blast could strip away atmospheres, alter orbits dramatically, and leave the surviving worlds circling within a system now ruled by a neutron star or a black hole instead of an ordinary sun. Even so, the planet endures. That's precisely what makes the idea so compelling. A world can outlive its own sun's violent death. In a real sense, it becomes a living witness to cosmic disaster, still quietly circling long after the very light source that once shaped its climate and sky has vanished forever. Survival on that scale feels almost mythic, a planet carrying on through an explosion that briefly outshone an entire galaxy, then simply continuing its silent orbit afterward, as though nothing had happened at all. We tend to imagine planets circling calmly above their star's equator, mostly because that's how our own solar system happens to be arranged. Yet some giant exoplanets break that expectation spectacularly. Their orbits are steeply tilted, and a few even pass almost directly over their star's poles, tracing paths that would look genuinely sideways compared with the neat, flat layout we're used to. This is one of the clearest signs that solar systems can undergo major upheaval over time. Orbits like these may be the direct result of violent gravitational interactions with other planets or with nearby stars, events that knocked a giant world clean out of its original orbital plane and left it circling instead at an astonishing, unfamiliar angle. The result feels deeply strange, because it turns an entire solar system from a calm, flat disk into a genuinely three-dimensional puzzle. A planet can rise up over a star's pole rather than simply sliding around its waist. Even orbital direction, something that once seemed almost fundamental and fixed, turns out to be yet another place where nature clearly likes to improvise. A planetary system, in fact, can look perfectly stable for millions of years, and then suddenly turn genuinely brutal. When several giant worlds happen to form together in the same young system, their combined gravity can begin a slow, ongoing contest of small nudges and near misses. One orbit shifts slightly, then another. A delicate resonance eventually breaks. A close encounter finally happens. And in that single dramatic moment, a planet may be hurled outward with such tremendous force that it escapes its star entirely. What was once a stable member of a settled solar family becomes, in an instant, a castaway. This kind of violent ejection may actually be one of the main ways rogue planets get made in the first place. It turns planetary history into something genuinely dramatic and precarious. A world can begin its life in a bright, young system full of heat, dust, and neighboring planets, and end up, eventually, drifting through interstellar darkness, simply because gravity became unstable for just long enough. That possibility makes every quiet, settled orbit feel a little less guaranteed than it first appears. A planet isn't always born to stay. Sometimes, it's born into a family that eventually throws it away. Sometimes a planet reveals itself not through light at all, but through gravity's own quiet fingerprint. If a star happens to pass directly in front of a more distant background star, its gravity bends and magnifies the background light in a very particular, measurable way. Add a planet into that foreground system, and the resulting magnification pattern shifts in a subtle, telltale manner. For one brief moment, gravity itself effectively becomes the detector. This is a wonderful kind of discovery, precisely because it feels so indirect and yet so precise at the same time. A world announces its own existence not by shining, but by quietly warping the geometry of light passing far behind it. Many of the planets found this particular way sit at considerable distances, difficult to study again or revisit, unlike the closer-in systems most other detection methods tend to favor. This approach genuinely expands the map. It reveals worlds through the sheer shape of gravity itself, as though each planet left behind its own signature on a beam of light passing quietly far away. One of the most productive ways astronomers have found exoplanets is also, in its own way, remarkably elegant. If a planet happens to cross directly in front of its star from our particular point of view, the star's light dips by a genuinely tiny amount. That brief, momentary dimming can reveal a planet's approximate size, its orbital period, and sometimes considerably more information besides. It's a delicate method, one that depends entirely on near-perfect alignment, which means the vast majority of planets never reveal themselves this way at all. But when one does, the effect is quietly profound. A world invisible in every direct sense suddenly becomes detectable, simply because it casts the smallest possible shadow across the face of its own sun. That shadow can repeat like clockwork, turning a faint, momentary blink in distant starlight into solid proof of an orbiting planet. There's something genuinely moving in that. We discover an entire world because, for one brief moment, it interrupts the light. A distant planet becomes known not through its own brightness, but through a tiny, rhythmic act of eclipse. A star, meanwhile, never truly sits perfectly still while a planet orbits around it. Both objects move together around a shared center of gravity, though the star's own motion is naturally much smaller and harder to detect. Astronomers can pick up on that motion as a subtle wobble, revealed through tiny shifts in the star's light as it moves gently toward us, and then away again. This particular radial velocity method was one of the very first great pathways into exoplanet discovery, and it remains genuinely important to this day. It gives astronomers not only the confirmed presence of a planet, but also a real clue to that planet's mass. The real beauty of this method lies in just how intimate the underlying physics feels. A planet far too faint to ever see directly can still make its own star sway. It leaves behind a subtle pull, quietly written into the star's own light. Which means an entire world can be found through influence alone, no shadow, no image needed, just a repeating, telltale signature hidden in the movement of a distant sun. The star, in effect, quietly tells on the planet by dancing, and astronomers have simply learned how to read its steps. Not every planet is found through starlight, either. Some are studied chiefly through their own thermal glow instead, especially young, massive worlds whose internal heat still leaks steadily outward as infrared light. This lets astronomers learn about atmospheres, cloud structure, and temperature without relying entirely on reflected light borrowed from a parent star. In a real sense, the planet introduces itself through its own warmth. That's a very different kind of discovery from a transit or a wobble. It feels closer to catching the actual body heat of a distant world glowing quietly in the dark. Planets like this are especially valuable because they can be studied in ways that more mature or smaller worlds simply can't. Their heat becomes a genuine source of information, revealing whether the atmosphere is cloudy, whether its chemistry varies from place to place, and how the planet is slowly cooling over time. A planet doesn't always need to block starlight or visibly tug on its star to be detected. Sometimes it's known simply because it's still quietly glowing, entirely on its own. Sometimes astronomers don't find a planet directly at all. Instead, they spot clear signs that something planetary simply has to be there. A disk of dust may show a sharp, unmistakable gap, as though an unseen world has carved a lane straight through the surrounding material. A ring may appear warped or noticeably asymmetrical. Gas may flow in patterns that suggest a hidden gravitational sculptor quietly at work. In more mature systems, the orbit of one already known planet may be slightly off from expectation, hinting strongly that another unseen companion is tugging on it from somewhere nearby. This is one of the most genuinely detective-like parts of modern astronomy. A planet leaves tracks without ever showing its face directly. It changes the environment quietly around it, and from those changes alone, astronomers can work carefully backward toward the unseen world responsible. It's a reminder that planets are agents just as much as they are simple objects. They carve, they pull, they disturb, and they organize. Even when we can't yet point directly to a planet itself, we may already be reading solid evidence of its presence, quietly written into the surrounding dust, gas, and orbital behavior. The phrase habitable zone sounds genuinely reassuring. It's simply the region around a star where temperatures might allow liquid water to exist on a planet's surface. But that phrase can be quietly misleading. A world can sit comfortably inside that zone and still be utterly hostile. If a planet's atmosphere is too thick, it may overheat entirely in a runaway greenhouse effect. If its star flares fiercely and often, radiation may hammer the surface relentlessly and strip away the air. If the planet happens to be tidally locked, one side may roast while the other freezes solid, unless the atmosphere manages to redistribute heat unusually well. Oceans, clouds, chemistry, and magnetic protection all matter enormously here. The habitable zone, in other words, isn't a promise, it's simply a starting point. That's part of what makes worlds like this so fascinating. They sit in exactly the right general neighborhood, while still stubbornly refusing to become gentle. A planet can inhabit the narrow band we once hoped for, and still remain a place where life, as far as we can reasonably tell, would face extraordinary odds from the very first moment onward. On some worlds, the difference between genuine possible habitability and complete hostility can come down to an extremely delicate balance of small planetary details. Thick clouds can reflect starlight away and cool a surface down. Tidal heating can warm a world that might otherwise have frozen solid. An atmosphere can carry heat from the scorching side of a tidally locked planet all the way over to the frozen side, gently softening extremes that would otherwise prove fatal. Remove any single one of these factors, and that very same planet might tip suddenly into disaster instead. This is one of the more beautiful complications running through exoplanet science today. Habitability, it turns out, isn't simply about raw distance from a star. It's about interaction. It's about whether a world can genuinely regulate itself, whether air, water, and heat can cooperate closely enough, for long enough, to create a truly stable surface. Which means some planets may live right on the very edge of possibility, their futures shaped by nothing more dramatic than the thickness of their clouds or the strength of a single tidal pull. A world can survive, in the end, simply because several subtle systems happen to work together quietly at the same time. Seen from a great distance, an ocean world can look genuinely serene. A smooth blue sphere, clouds drifting gently above a single global sea. It's exactly the sort of planet that invites easy hope. And yet, up close, that same beauty may conceal deeply hostile conditions underneath. The ocean itself could run hundreds of miles deep, with no land anywhere at all, and pressures that rise, far below, to levels almost impossible to imagine. The atmosphere above might be dense, acidic, or thick with greenhouse gases. Beneath the upper water layers, high-pressure ice could trap the deep ocean completely away from the rocky interior below, cutting off exactly the kind of chemistry many scientists believe life might genuinely require. Storms could sweep unchecked, endlessly, around the entire globe. What makes worlds like this so gripping is precisely how they blur the line between inviting and dangerous. They resemble paradise in outline, but perhaps not at all in substance. A planet can look soft and genuinely life-friendly in silhouette, while quietly hiding conditions far more severe than any sea, storm, or abyss our own world has ever known. Beyond questions of chemistry and climate, some worlds would simply feel physically alien in the most basic bodily way. Gravity shapes lived experience far more than we usually stop to notice. On Earth, every step, every jump, every fall unfolds within a familiar, dependable pull our bodies have known intimately since birth. But on some exoplanets, especially the larger rocky super-Earths, gravity could be considerably stronger than anything we're used to. A simple walk might feel like a constant, uphill climb. Lifting your own arm could quickly become exhausting. Jumping would lose nearly all of its upward freedom. On lower gravity worlds, meanwhile, the opposite would hold true. Falls would feel gentler, movement springier, every motion just slightly untethered from the ground. This matters because it's a quiet reminder that a planet isn't only defined by its atmosphere or its temperature. It's also a direct, physical conversation with the body. Gravity tells you exactly how heavy your own bones feel, how quickly you tire, how a tossed stone arcs gently through the air. Some worlds may look broadly Earth-sized on paper, in some distant catalog, and yet the lived sensation of actually standing on one would feel utterly, completely strange. Even the simple act of standing still could feel like stepping into an entirely different kind of physics altogether. At a certain point, the word planet itself starts to feel almost too mild for what some of these worlds actually are. Some exoplanets are so hot, so heavily irradiated, and so physically transformed by their sheer proximity to their star that they genuinely resemble industrial furnaces more than places in any ordinary sense. Their atmospheres may contain vaporized rock or vaporized metal. Their permanent daysides may glow with heat intense enough to melt solid crust outright. Their winds may race at genuinely terrifying speeds, high above chemical conditions that no earthly weather system could ever hope to match. Calling a world like this a planet is technically correct, but the word doesn't quite convey the full weight of what it now has to hold. These aren't gentle spheres quietly orbiting some distant sun. They're active thermal systems sitting directly under savage, relentless energy input. Part of the fascination lies precisely in that mismatch, in a familiar category stretched right up until it very nearly breaks. A planet can still, technically, remain a planet, and yet feel, in spirit, considerably closer to a forge or a kiln or a contained blast of pure stellar punishment than to anything we'd ever comfortably call a home. Again and again, astronomy has quietly followed the very same pattern. First comes the confident assumption that a certain kind of planet would simply be too strange, too unstable, or too unlikely to actually exist anywhere. Then comes the discovery that nature went ahead and built it anyway. Giant planets skimming impossibly close to their stars. Worlds circling the corpses of dead pulsars. Planets with densities so low they initially seemed almost absurd. Rocky bodies with entirely molten faces. Systems packed far tighter together than theory once comfortably preferred. This is one of the deepest, most quietly satisfying pleasures in the whole field. The universe keeps steadily outgrowing whatever imagination we use to try to predict it. Telescopes turn yesterday's impossibility into today's solid data, and the growing catalog of known worlds slowly becomes, in its own way, a history of gently corrected expectations. That's exactly why these strange planets feel so powerful to sit with. They're not only fascinating places in their own right, they're quiet reminders that reality is simply larger than human comfort allows for. Every time a world once considered unlikely turns out to be real, the cosmos opens up just a little wider, and our own private sense of what's possible has to gently make room for it. For all the astonishing worlds already known and carefully cataloged, we remain, in truth, still very early in this particular story. Our current detection methods naturally favor certain kinds of planets over others. We're best, for now, at finding large worlds sitting close to their stars, or special systems that happen to align just right for our instruments. Which means the existing catalog isn't the full truth of planetary diversity out there. It's really only a first draft, shaped almost entirely by what current technology happens to see most easily. Somewhere beyond that quiet bias may lie worlds even stranger than any we've already found. Planets with combinations of chemistry, orbit, and structure we haven't yet even imagined. Systems built in ways our current theories barely hint at. This is exactly what makes the whole subject feel genuinely alive, rather than finished. Discovery hasn't narrowed the universe down at all. If anything, it's made the hidden portion of it considerably more tantalizing. The strangest planet of all may not even be famous yet. It may still be quietly waiting out there in the dark, entirely untouched by our telescopes, simply waiting patiently for its turn to overturn the picture one more time. We've wandered a long way together tonight, far beyond the familiar worlds of our own solar system, into a cosmos filled with metal rain, molten seas, wandering rogue planets, and skies lit gently by two suns at once. We've passed through worlds stretched by gravity, worlds hidden beneath endless steam, and worlds so hot that solid rock can melt and rise directly into the air. We've imagined deep ocean planets with no shore anywhere at all, dark planets that quietly swallow starlight, and distant young worlds still glowing softly from the sheer violence of their own creation. And perhaps that's the most remarkable part of all. The universe isn't only larger than we once believed. It's stranger, richer, and considerably more inventive too. Out there, far beyond the reach of our hands, entire worlds drift on in silence, each one carrying its own weather, its own particular light, its own long and quietly hidden story. Some may glow softly, like embers. Some may sleep on, entirely in darkness. And some may still be waiting, patiently, for us to find them. But for now, you don't need to travel any farther tonight. Let the stars grow soft in your mind. Let those distant, strange skies fade gently into darkness. Allow your breathing to slow, and let the weight of the whole day slip quietly away. You've gone far enough for one night. The universe will still be there tomorrow, vast and waiting, with all its strange and beautiful worlds still quietly turning in the dark. From all of us here at Somniora Mind, rest now. You've earned it. Good night.